All right, so welcome back, everybody. Today we're going to continue on with our lecture on quantum mechanics, and this will actually be the last video in the series. So in the previous video, we talked about the position, momentum, uncertainty principle, which is the idea that you can't perfectly know the position and momentum of a particle at the same time because they're actually not both well defined at the same time. And we're going to talk about a similar idea today, which is the energy-time uncertainty principle. So here's what it says. It's all encapsulated in this inequality here. And it says delta E times delta T is greater than or equal to h bar over 2. So what this is saying is the product of the uncertainty in the energy of a quantum state, that's the delta E part of this, times the uncertainty in the lifetime of that quantum state, that's the delta T part, is at minimum h bar over 2. So the way you want to think about this is, if we think about these two uncertainties, delta E and delta T, as one of them gets smaller, the other one is going to have to get bigger. So for example, if delta T gets smaller, delta E is going to have to get bigger. So another way of saying that is, the shorter lived the quantum state is, the smaller delta T is, the more uncertain its energy will be. That is, the larger delta E is going to have to be. So I want to give you an intuitive feel for this idea. We're not going to prove this rigorously. It's a little bit outside of the scope of the class to do that, but I want to give you sort of an intuition for why this should be true. So let's recall that energy is related to frequency. We remember that E is equal to h bar times omega. So E is the energy of some particle, h bar is just Planck's constant in the reduced form, and omega is the frequency with which its wave function oscillates. Okay, so the idea here is, if we can only observe a wave for a short period of time, we're going to be pretty uncertain about what its frequency is. And therefore, we're going to be pretty uncertain about what its energy is, because again, energy is just directly related to frequency. So I'm going to show you two different waves. In the first one, we can see the wave as it oscillates for many, many cycles. So you should be interpreting what's on the horizontal axis here as time. So we're sort of plotting the wave out against time, and we're seeing many, many cycles of its oscillation, right? So this would be an example of a large delta T. In other words, a quantum state that lasts for a very long time. And in that case, the frequency is quite well defined, right? Because we can easily see what the frequency is since we've observed many, many cycles. Now, on the other hand, if we look at this wave over here, we're only seeing like a fraction of a cycle. Delta T is quite small, and we have a lot of uncertainty about what the actual frequency is, right? We need to observe a whole lot of cycles to actually precisely determine a frequency. So in this case, the frequency is not very well defined, and therefore we have a lot of uncertainty about what the energy is here. So again, remember what we said. The shorter lived a quantum state is, the more uncertain its energy is. That's what's going on here. It's a very short-lived quantum state. We can barely observe it for, a fraction of a cycle, and we're very uncertain about what its energy is as a result of that. So let's do an example of this. In this example, we have an electron, which is in a sodium atom, making a transition from the first excited state down to the ground state. And it does so by emitting a photon with a wavelength of 589 nanometers. And the energy of this photon is 2.105 electron volts. If the lifetime of this excited state is 1.6 times 10 to the minus 8 seconds, what is the uncertainty in the energy of the electron in this excited state? And we'll give this in units of eV. And then as a follow-up, what is the frequency and the uncertainty in the frequency of the emitted photon? All right, so again, the picture you should have is this. We have an electron, which is in the excited state. I'll call that E2. And it's only in that excited state for a very short time. That's the lifetime given here. And after that lifetime, it drops down to the ground state, and it does so by emitting this photon. So let's work this one out. Okay, so we'll start with the energy-time uncertainty relationship, which says delta E times delta T is greater than or equal to h bar over 2. And for delta T, let's just make a note, we're going to set this equal to the lifetime of the quantum state, which is 1.6 times 10 to the minus 8 seconds. So this excited state that the sodium atom can be in, it only lasts for a really short amount of time. Okay, so delta E, if we solve for that, is greater than or equal to h bar over 2 times delta T. Now that's an inequality, but we can see that the minimum value that delta E can take on is just h bar over 2 times delta T. So we're going to use that to make an estimate of delta E. So remember, delta E is the uncertainty in the energy of our quantum state. Okay, so we have h bar. Remember, h bar is the same as h over 2 pi. So we're going to have 1 over 2 pi times h, which is 6.626, 10 to the minus 34 joules times seconds. Remember, that's Planck's constant. And then we divide that by, we have 2 times delta T. So that's 1.6, 10 to the minus 8 seconds. Okay, what this comes out to, if you do the calculation, is 3.296, and then times 10 to the minus 27 joules. And we'll keep actually 2 sig figs on that. But before we give the answer, let's convert it over to electron volts. Okay, so 1 electron volt is the same thing as 1.602 10 to the minus 19 joules. So that's what we're going to use to make the unit conversion. And if you do that calculation, it's 2.1 times 10 to the minus 8 electron volts. So that's a pretty small uncertainty in the energy, but it's not zero. Okay, now let's think about the frequency of the emitted photon. So remember, this sodium atom is jumping from an excited state down to the ground state, so it's emitting a photon. What's the frequency of the emitted photon? Well, since we know the wavelength of the emitted photon, there's a pretty simple way we can do this. We can just say c, the speed of light, is equal to lambda times f. That's wavelength times frequency. And we can solve for f. So f is equal to c over lambda. All right, so c is 3 times 10 to the 8 meters per second. And lambda, this was given in the problem, is 589 nanometers. So that's 10 to the minus 9 meters. All right, so if you do that calculation, it'll come out to 5.093 times 10 to the power 14. And the units here are inverse seconds. And if we round that to 3 sig figs, which is what we should do, we should have 5.09, 10 to the 14, and inverse seconds is the same thing as hertz, so we might as well say this is in units of hertz. So that's the frequency of our photon, and by the way, that's in the visible range, so you'd be able to see this photon. The last thing we'll do here is, what is the uncertainty in the frequency of, the emitted photon? So same as before. So for this, maybe one way we could tackle this is by saying, look, the energy of our photon is equal to h times f. So it's the Planck's constant times the frequency. From this, we can see that the uncertainty in our energy is equal to h times the uncertainty in the frequency. So delta E is equal to h times delta f. Now, if we want to know what delta f is, this is going to be delta E divided by h. Okay, so delta E is what we found before. Let's take this value of it that's given in joules, and we'll do the calculation that way. So what do we have? We have 3.296, 10 to the minus 27 joules, divided by h, which is Planck's constant, 6.626, 10 to the minus 34 joules times seconds. And again, we have inverse seconds or hertz as the unit. This comes out to, if you round it off, 5.0 10 to the 6 hertz. So if we compare the frequency of the emitted photon here to the uncertainty in the frequency, the uncertainty is pretty small, but it is there. And what that means is when this atom makes a transition from the excited state to the ground state, the frequency of the photon that it emits is not always going to be exactly the same. There's going to be a range of frequencies that get emitted. It's a really small range because, again, our uncertainty in the frequency is very, very small compared to the frequency itself, but there is some range there. And if we think about what this means in terms of our emission spectra, remember, we can study the type of light that atoms give off by studying their spectra. And we remember these spectra consist of different lines, right? These emission lines are not just infinitely thin. Instead, there's some kind of thickness. There's some sort of width to them because of the fact that, again, there is a range of frequencies present within this line. So without the uncertainty principle, we would expect just an infinitely thin line. But because of this uncertainty principle, the line has some thickness to it. Okay, so now here is one for you to try out. The Higgs boson is an unstable particle that has a mass of 2.23 times 10 to the minus 25 kilograms and an average lifetime of 1.56 times 10 to the minus 22 seconds. So what that means is it will typically take 1.56 times 10 to the minus 22 seconds for the Higgs boson to decay into other particles after it gets created. So if you create this particle, the Higgs boson, in a lab, it's not going to stick around for very long. In a very short time, it's going to decay into other things. So with that said, what is the minimum uncertainty in the energy of the Higgs boson? We're going to do this in units of joules first and then convert it over to eV. And then using Einstein's famous equation, E equals mc squared, try to estimate the uncertainty in the mass of the Higgs boson in units of kilograms. So the idea here is if we have some uncertainty in the energy, we should also have some uncertainty in the mass. We don't have to really understand this equation deeper than that. Let's just use it to make the calculation. Okay, and then lastly, what is this uncertainty as a percentage of the Higgs boson mass? So in other words, if we compare the uncertainty in the mass to the actual mass itself, what is the percentage? So pause the video, try to find the answers to these questions, and then we'll go through it together. So we'll start this one by writing down the energy time uncertainty relationship. So that's delta E times delta T is greater than or equal to h bar over 2. So just like before. And we want to solve for delta E, and in particular, the minimum possible value for that. So that's just going to be equal to h bar over 2 times delta T. So same calculation as before, but what's different is the lifetime delta T is really small compared to before. So what happens? H bar is 1 over 2 pi times 6.626 times 10 to the minus 34 joules times seconds. And we divide that by 2 times delta T, where delta T is 1.56, 10 to the minus 22 seconds. That's the lifetime for the Higgs boson. Okay, if you calculate that, it comes out to 3.38 times 10 to the power minus 13 joules. And we can quickly convert that over to electron volts using the unit conversion 1 eV divided by 1.602, 10 to the minus 19 joules. Okay, so what does this work out to? If you do the calculation, it's 2.11 times 10 to the 6 eV. So remember, 10 to the 6 is the unit prefix mega, and we can write this as 2.11 mega electron volts, MeV. Now that's a much larger uncertainty for the energy than we got before because of the fact that delta T is so small compared to before. Okay, so we have this uncertainty in the energy of the Higgs boson. We can estimate the uncertainty in the mass of the Higgs boson if we use this relationship. E equals mc squared. This is Einstein's famous equation. And basically what this is saying is there's some equivalence between energy and mass. This also assumes that the particle is not really moving, but let's put that to the side. If we take this formula and we say on the left-hand side, I want to solve for delta E, then on the right-hand side, I will have I'll have delta M times c squared, which is just a constant. So we can see that delta M, the uncertainty in the mass, is equal to delta E, the uncertainty in the energy, divided by c squared. So what's delta E? Delta E is, like we just said, 3.38 times 10 to the minus 13 joules. And c is the speed of light. So that's 3 times 10 to the 8 meters per second, and we square that number. And if you do this calculation, actually, before we do that, let me just change the units up here. Instead of joules, I'm going to write that as kilograms meters squared per second squared. And the reason for that is when we do that, it clearly comes out in units of kilograms. So the uncertainty in the mass is equal to 3.76 10 to the minus 30 kilograms. Okay, so because the Higgs boson only lasts for a short time, there's not only some uncertainty in what the energy is, but there's also some uncertainty in terms of what the mass is. And we can write this as a percentage like this. We're going to do delta M over M, that's the uncertainty in the mass divided by the mass, times 100 to make it a percentage. And here's what we get. 3.76, 10 to the minus 30 kilograms. That's the uncertainty we just found. The mass, which is given to us, 2.23 times, what is the power? 10 to the minus 25 kilograms. Multiply by 100. And now we have a nice percentage. So this is 0.00168%. So we're always about this uncertain about what the mass of the Higgs boson is in terms of a percentage. Okay, so at this point, we've covered basically all of the quantum physics that you're going to see in this class, but it's worth taking a step back and pausing for a second just to think about what it all means, okay? Because quantum mechanics is a very strange theory. A lot of it is very counterintuitive, and you might be able to even use it pretty well, like solve the equations, get the right answers, but still be unclear about what it actually all means, okay? And that's where we have to think about how to interpret quantum mechanics. Now, we're going to touch on some pretty philosophical issues here, and even touch on some issues that are still hotly debated, and physicists disagree about them. So let's get into it. How should we interpret quantum mechanics? And the first topic I want to touch on here is the correspondence principle. This is all about how classical mechanics relates to quantum mechanics. Of course, they're very different types of theories, so how should we think about the way they go together? Okay. So the way we want to think about this is classical mechanics is just an approximation of quantum mechanics. It works pretty well to describe macroscopic systems. So for example, you could use an equation like F equals ma to describe how a box slides down a ramp, or how your car drives, or how a projectile flies through the air, things like that. But it's going to break down if you try to apply it to a microscopic system. It just doesn't work anymore. And that's why in the early 1900s, there were all these problems like, the photoelectric effect and blackbody radiation, where classical physics just wasn't working anymore. So this picture down here gives you a nice way of visualizing what I'm talking about. So this blue box, that's meant to represent everything that quantum mechanics is able to explain, okay? And because quantum mechanics is sort of a broader theory, it's in some sense it's more correct, it can explain both physics on the microscopic level and the macroscopic level. So quantum mechanics explains a broader range of things, whereas classical mechanics is a little bit more limited, and that's represented by this red oval. It can only explain a more limited range of things. That is only the physics of the macroscopic world, okay? But there is some range where they overlap, right? And where the two theories do overlap, they agree. They have to give you the same answer, okay? So in other words, if I try to take classical mechanics and apply it to a microscopic system, it's just not going to work, okay? But if I try to take quantum mechanics and apply it to a macroscopic system, it should work, and not only that, it should give you the same exact answer as classical mechanics. So these are two theories. They kind of have different domains over which they apply, but where those domains overlap, the theories agree. So in particular, if we want to be a little more technical about this, we say if your system has a large n value, that's a large quantum number, like I'm talking about the n values that you use to calculate energy, things like that, the predictions of quantum mechanics and classical mechanics should agree. And I'm going to give you an example of this, okay? Here's the example. Consider a mass spring system where the mass is 2 kilograms and the spring has a K constant of 230 newtons per meter. This thing is oscillating with an amplitude A, which is 1 centimeter. What is the energy of this oscillation? And then what is the quantum number? What is n? And then let's finally calculate what is the spacing between the energy levels of this oscillator. Okay, so this is clearly a case where we're in sort of the classical mechanics realm. This is a macroscopic object that's oscillating around. But we can still use quantum mechanics to calculate things like, the energy levels. So we're going to do that, and we're going to see that it actually looks a lot like the classical mechanics we've seen before. So let's go through it. Okay, so what we're dealing with here is a harmonic oscillator, and we can calculate the frequency omega for that oscillator by using the formula omega is equal to the square root of k over m. Now in this case, k is equal to 230. The units are newtons per meter, but I think I showed you this before. That's equivalent to a kilogram per second squared, so I'm just going to write it that way. And then the mass m is 2.0 kilograms, and then we'll have to square root that whole thing. All right, so if you calculate the result, it's about 10.7 radians per second. We'll actually keep 2 sig figs on that at the end of the day. Okay, another thing we can calculate is the energy. What is the energy of this oscillator? Well, it's given by, we can write this as 1/2 k times a squared, or we can write it as 1/2 m times omega squared times a squared. Either way is fine. And we can use that to calculate the total energy of our oscillator. So let's do that. We have 1/2. What is the mass? It's 2.0 kilograms. And omega, that's 10.7 radians per second, which we just found. And then A is the amplitude. So this particular case involves something oscillating with an amplitude of 1 centimeter, which is the same as 1.00, 10 to the minus 2 meters. And we're going to square the amplitude. And if you do the calculation, this comes out to 0.0114, and the units are kilograms, meters squared per second squared, so that's a joule. So to round it off, it's about 1.1, 10 to the minus 2 joules. So that's the energy we're dealing with. Okay. The next thing I want to do is bring in a formula we derived for a quantum harmonic oscillator. So I'm just going to write QHO for quantum harmonic oscillator. And this formula says that the energy of our oscillator is equal to n plus 1/2 times h bar omega. So we're trying to calculate n. That is the quantum number of our system here. So we can do that. That's pretty straightforward. First, let's divide out the h bar omega. So we have n plus a half equals E divided by h bar omega. So if we want to find n, we could just subtract off the 1/2, right? So it looks like n is equal to E divided by h bar omega minus 1/2. But what we're going to find is this is such a huge number that subtracting off a half makes like absolutely no difference. But anyway, let's do the calculation. We have the energy, which we just found is like 1.14, 10 to the minus 2, and the units on that thing are joules, right? And then we divide out h bar. So remember, h bar is 1 over 2 pi times h, where h is 6.626, 10 to the minus 34, and the units are joules seconds. So that's h bar. Put that in parentheses. And then we have omega. That's 10.7 radians per second. And then, yeah, you could subtract off the half, but again, it makes no difference. All right, what does this come out to? 1.01 10 to the 31st power. So that the quantum number, okay, is 10 to the 31st power. So if we think about like the n values and what they mean, you know, n equals 0 is the ground state, n equals 1 is the first excited state, and then you can just keep going with that. Here we're saying n is equal to 10 to the 31st power. So that is a super large value of n. We're very, very far away from the ground state. And that's what we would expect for, again, like a macroscopic object, right? Okay. So I believe the other question we wanted to answer here was, what is the spacing between energy levels of this oscillator? So the spacing between energy levels is actually just h bar omega. And that's something we can calculate again. So h bar is, what is it? It's 1 over 2 pi times 6.626, 10 to the minus 34 joules times seconds. And then we have 10.7 radians per second. So this comes out to 1.13 times 10 to the minus 33 joules. Okay, so what I really want to compare here is the spacing between the energy levels that you see like this with our delta E value and our actual energy, which is the first thing we calculated. We might just take the ratio of those two. That's a nice way of comparing them. If we took E divided by delta E, just divide those two numbers out, yeah, you get, again, something like 10 to the 31 power. Okay, so what this is saying, let me just put it in words, is the energy of the oscillator is much, much, much bigger than the spacing between energy levels. And for all intents and purposes, we don't even notice that there's any spacing between the energy levels. To us, it just looks like a continuous range of energies. In other words, we don't really notice that the energies are quantized, which is just to say that it looks just like in classical physics. With a classical harmonic oscillator, you know, there's no restrictions on the energy values you can take on. They're not discrete energy values. You can just take on any value of energy that you like. And in the quantum harmonic oscillator, the energy levels are discrete with gaps in between, and you can't take on energies in between the given energy levels. But even though that's still technically the case, the point is the spacing between energy levels is so tiny that you don't even notice it. And it looks just like our familiar classical harmonic oscillator. So that's what I'm trying to get across here. So here's a question for you guys to think about. Quantum mechanics and classical mechanics are radically different theories, but their predictions agree when they're applied to a macroscopic system. This is known as the correspondence principle. That's what we were just talking about. Quantum mechanics is a broader theory, however, because it also accurately describes the microscopic world. So what this really means is anything that can be explained by classical mechanics can, at least in principle, be explained by quantum mechanics. So my question for you is, why do we still use classical mechanics and is it obsolete? So pause the video for a second just to think about this, maybe jot down a few of your thoughts, and then I'll come back and give you my thoughts. Okay, so the simple answer here is we still use classical mechanics because it's easier, okay? It's easier to use. And if we can use the easier theory, we should probably do that just for convenience, right? It would be unimaginably difficult to try to use quantum mechanics to predict, how my car is going to drive down the street. It's, in principle, you could do it, but in practice, you would never want to do that. You would want to just use classical mechanics. It's much simpler and it works really well, at least if you apply it to the right scenario, which is a macroscopic system. So why wouldn't you do that? We don't have all day to sit around and calculating things when we have easier tools available for us. However, if we want to describe the microscopic world, you're stuck with quantum mechanics because that's the only thing that works. So I hope you remember the double slit experiment. This is something that we talked about a lot during our unit on light, but we're going to be seeing a slightly different version of it here today. So rather than having something like a laser firing a beam of light towards the slits, we're going to be sending particles one at a time towards the slits. So let's imagine this is our electron beam gun, and it fires electrons one at a time in this direction. Okay, so we have electrons coming out one at a time heading towards the slits. After going through the slits, they hit this screen over here. And this screen kind of acts like a detector because wherever a particle hits the screen, it's going to leave a little dot. So over time, if we send many, many electrons through, we're going to have many, many hits on this screen, and we're going to see many, many dots start to accumulate on that screen. So the question is, what kind of pattern is going to build up with those many, many hits on the screen? The surprising thing is that you start to see an interference pattern. Okay, an interference pattern, just like we saw with light, starts to build up on the screen, looking something like this. We have a bright line in the center where we have a whole bunch of hits, and then we have another line next to that where there are slightly less hits, and so on. That is not what you would probably expect. You'd probably expect just to see two lines, one behind each slit, because of course, if you go through this slit, you'll hit over here, and then if you go through this slit, you'll hit over here. The fact that we're getting this interference pattern is actually telling us that somehow each particle is going through both slits at the same time, because you need interference to have an interference pattern. And that means you need a wave coming out of both slits at the same time and interfering with each other in order for this pattern to start building up. So that's pretty weird. But the technical way of saying this in terms of a wave function is like this. The wave function should be thought of as a superposition of having gone through the left slit and having gone through the right slit. So your system is in a superposition of those two states. And that's why you get interference when you hit the viewing screen. But it gets even weirder than that, because what we can do is place a detector right where the slits are. And basically what that detector is going to do is tell us which slit did each particle go through. Did it go through the one on the left, or did it go through the one on the right, or did it somehow go through both? If we place that detector here, what happens is we no longer have an interference pattern building up. With the detector telling us which slit the particles are going through, we get this pattern emerging, where again, it's just a single line of hits behind the right slit and then a single line of hits behind the left slit. So it's pretty weird that you get a completely different outcome for this experiment if you have a detector at the slits versus if you do not have a detector there. And it actually points to a much larger problem in quantum mechanics called the measurement problem. So here's the idea. Prior to a measurement, the wave function for a particle is in a superposition of different states. And that wave function evolves according to the Schrödinger equation. However, at the moment when we make a measurement, the particle randomly collapses into some kind of definite state. So as an example, we never find a particle to be in two different locations when it's measured. Prior to measuring it, it can be in a superposition of being in those two different locations, but when we actually do the measurement, we always find it in one definite location. So that raises a whole bunch of questions. For example, why is it that when we make a measurement, we destroy the superposition? We go from being in a superposition of states to being in one definite state. And then what does it actually mean to make a measurement on a quantum system? What constitutes a measurement? And then the last question here is, are measurements made by humans actually part of the fundamental laws of physics? Because that would be pretty weird. So let's try to address all these different questions. So we'll start with this. Are measurements made by humans really part of the fundamental laws of physics? Let's address that question. The answer is almost certainly no, and the reason for that is something called decoherence. So quantum decoherence is an idea that was first proposed in the early 1970s by a German physicist named H. Dieter Zeh. And basically what he showed is that when a quantum system starts off in a superposition of many states, it's very quickly going to evolve into a single definite state if it interacts with its larger environment. So in other words, there's something about a quantum system interacting with its larger environment that destroys the superposition. It has nothing to do with like a human observer watching the system or a human scientist making a measurement. It's just the fact that the quantum system interacts with its environment. And so just to give you an example of this, there's nothing really human about it, even an atom colliding with another atom can take it out of a quantum superposition, right? If one atom bumps into another, it can prevent it from being in a superposition of states. So it's not really about humans making measurements. It's really more about systems interacting with their environments. But there's still a whole lot of unresolved questions, even if we understand this idea of decoherence. And the main question that's still unanswered is, what is physically happening when a wave function goes from a superposition of many different states into a single definite state? So there are a lot of different points of view about this, and none of them are definitively correct. And I can only list a few of them. There are a lot of other points of view out there other than what I'm going to list here. But just know that this is something that's still hotly debated in physics. Like, how should we interpret the collapse of a wave function? So the first one is the Copenhagen interpretation. And this was one that was advocated by people like Niels Bohr back in the day. And I think it basically boils down to shut up and calculate. Because according to this point of view, quantum mechanics works really well. If you use it to make calculations, you'll get the right answers. So why worry about these philosophical questions, right? I tend not to like that point of view so much because I really do want to have a good picture in my head about what's going on. So then you have some pretty outlandish seeming ideas like the many worlds interpretation. And according to the many worlds picture, the wave function actually doesn't collapse. Instead, what happens is the wave function for the entire universe splits into different parallel branches. And every single possible outcome does happen just along one of these different branches. So let me give you an example of this. What's shown down here in this picture is the famous Schrödinger's cat situation, where we have a radioactive atom, and if that radioactive atom decays, it's going to set off a whole sequence of events where some poisonous gas will be released, and it will kill the cat. On the other hand, if this radioactive atom doesn't decay, then the cat will stay alive, okay? and that radioactive decay of the atom is a completely random process, and it's dictated by quantum mechanics. So basically, what happens at the quantum level is tied to what happens to the cat. So according to the many worlds interpretation, what happens is the world splits into two branches. Along this branch, the radioactive atom does decay, and then the cat dies. And then on this other branch, the radioactive atom doesn't decay, and the cat stays alive. And both of those things just happen. They happen along different branches. And of course, you can only exist in one of those branches, so you don't see all the different possibilities happening. But according to this point of view, every single possible outcome does happen, just in some other parallel universe. So that sounds a little weird, but it is actually something people take seriously in physics. Then we also have things like pilot wave theories. So in a pilot wave theory, each particle has an associated wave. There's literally a wave there and a particle there. And the particle kind of rides along the wave, and the wave determines the trajectory of that particle and where it's going to move. And again, these are just different interpretations. They all could potentially work, and there's not really a consensus as to what the proper way to interpret quantum mechanics is. We can agree what the equations are and what they're saying and what we can calculate from them, but we don't always agree on how to interpret those equations. So another interesting feature of quantum mechanics that I want to tell you about is something called quantum entanglement. So quantum entanglement is when a system of two or more particles can only be expressed as a single wave function and not by separate wave functions for each particle. So in other words, what one particle is doing is entangled with what the other particle is doing, and you actually can't separate them out and describe them with separate wave functions. So let me give you an example of this. So if two photons are emitted by a system with no overall angular momentum, the spin of the photons must be in opposite directions. So when we say spin, we're just referring to a type of angular momentum that the photons carry with them. So the whole idea behind this is that angular momentum is conserved. If the source of those two photons, the system that's emitting the photons, has no overall angular momentum, that means the photons together must have no overall angular momentum. In other words, the angular momentum of one photon has to be canceling out the angular momentum of the other. Another way of saying that is their spins are in opposite directions. In quantum mechanics, we tend to indicate spin with an arrow that can either face up or down, meaning spin up or spin down. So one possibility is that, let's call this one photon A. If photon A is in the spin up state, then photon B has to be in the spin down state. And if photon A is in the spin down state, that means photon B has to be in the spin up state. They have to be in opposite spin states. So with that as our setup, we can write the wave function for the two photons together. And it looks something like this. Alpha 1, which is just some kind of coefficient, some kind of constant, times spin up, spin down, plus alpha 2 times spin down, spin up. What this is saying is that the system can be in a superposition of two states. The first state is A is spin up, B is spin down, and the other state is A is spin down and B is spin up. So in general, it can be in any superposition of those two possible states because they both involve the two spins being in opposite directions. Okay? So let's now think about what happens if we measure the spin of one of those photons. Okay? If we measure the spin of one of those two entangled photons, the other one is instantaneously going to have to collapse into the opposite spin state. So for example, let's say we go ahead and we measure the spin of photon A, and we determine that it's spin up. That's basically going to force photon B to go into the spin down state. Again, they have to have opposite spins. And keep in mind, this has to be true regardless of how far apart the two photons are. So for example, to give you a really extreme case, let's say I have two photons, A and B, and photon A happens to be passing by my laboratory. So I go ahead and I measure the spin state for photon A. Photon B, let's say, is on the opposite side of the universe. It's really, really far away. So as soon as I make my measurement on photon A, it instantaneously determines what the spin state of photon B is going to be. Again, even if it's like on the opposite side of the universe. Now, that should strike you as weird because normally in physics, we don't expect that one object can influence another object instantaneously at such a great distance, but that's what quantum mechanics is telling us if we're taking it seriously. So you might just wonder, okay, maybe each photon already somehow knows what it's going to do when you make a measurement of it. So like the result that it was going to give was already determined from the beginning. This idea is called hidden variables. The idea that the particles contain some sort of hidden information that determines what result they're going to give when you measure them. Experiments have pretty much ruled that out as a possibility. What we now know is that entangled particles are truly in an indefinite state before they're measured, okay? So there's no definite state before you measure them. It's only when you measure them that they go into some sort of definite state, like spin up or spin down. And again, the state of one instantaneously determines the state of the other, even if they're separated by a huge distance. It's weird. It's really, really weird, but that's just the reality we live in. That's how it works. And so the latest Nobel Prize in Physics, the 2022 Nobel Prize, was actually awarded to 3 researchers who did work on quantum entanglement. Okay, so we're going to end it with this. We're going to talk about some of the modern developments in quantum mechanics. So let's start by talking about the successes of quantum mechanics. Quantum mechanics is a hugely successful theory. You could probably argue that it's the most successful theory ever produced in any field of science. And let me just give you some bullet points to sort of back up that argument. So first of all, quantum mechanics has been tested countless times, and there's never been an experiment that has shown a conflict with the basic principles of quantum mechanics. So essentially, it's passed every single experimental test for over 100 years. Also, quantum mechanics is super accurate. The predictions of quantum mechanics agree with experiments up to 10 significant figures in some cases. Now really think about that. Imagine you're doing a lab and you measure something, okay? That's your experimental result. And then you calculate something, that's your theoretical result. Have you ever been in a lab situation where those two numbers agree to 10 significant figures? Because that's what's going on with quantum mechanics in some cases. So really close agreement between theory and experiment. Also, quantum mechanics pretty much underlies all of chemistry, okay? If we understand quantum mechanics, we can explain essentially every feature of the periodic table of elements. And that's really amazing because all we have to do is solve the Schrödinger equation for an atom and solve for the electron orbitals within that atom. And we can understand electron shell structure. We can understand things like electronegativity and a whole bunch of other things that you see on the periodic table. It's all underlied by quantum mechanics. And then finally, there's a whole lot of technologies that rely on quantum mechanics that we use in our everyday lives. Things like solar cells, MRI scanners, lasers, transistors. There's a whole lot more I could list there. But I think it's safe to say that quantum mechanics is the most successful theory that humans have ever come up with. So the standard model of particle physics is the culmination of many decades of work in quantum mechanics. And it basically encapsulates most of what we know about the universe at the most fundamental level. It describes all of the known fundamental particles, These are the particles that we think can't be divided into smaller parts, as well as 3 out of the 4 fundamental forces. These include electricity and magnetism, the strong nuclear force, and the weak nuclear force. But notice the 4th fundamental force, gravity, is missing from the standard model. So what does the standard model actually look like? Well, we have different particles which are arranged in groups. So the quarks and the leptons make up all of the matter around us. The quarks come together to form things like neutrons and protons, whereas if you notice, the electron is in the lepton group. So leptons are an important part of atoms, as well as the quarks that make up the nuclei of the atoms. Then we have the gauge bosons, which are responsible for transmitting forces between different particles. So for example, we have the photon, which is responsible for transmitting the force of electricity and magnetism. We have the gluon, which is responsible for the strong nuclear force, which holds things like protons and neutrons together. And we have other gauge bosons too, but that's the basic picture. We have quarks and leptons making up the matter, and the gauge bosons, which are responsible for transmitting the forces between different particles. So the standard model is based on quantum mechanics. It's just based on a more modern version of quantum mechanics, which is called quantum field theory. So in quantum field theory, or QFT for short, the state of the universe is still described by a wave function, just like in old school quantum mechanics. However, now the wave function is not a function of things like position or momentum. It's a function of the values of various fields that exist in space. So for example, the electric field. And in QFT, particles are kind of demoted to a lower status. QFT treats particles as just excited states of some underlying quantum field. And those quantum fields are more fundamental than the particles themselves. So let me give you an example of this. In quantum field theory, there's something called the electron field, okay? And the electron field exists at every point in space. If at some point in space there's an excitation in the electron field, that just corresponds to an electron being located there. So in other words, particles are just excitations in their underlying fields, according to quantum field theory. And this is the more modern version of quantum mechanics. So as I mentioned before, the standard model of particle physics includes almost everything that we know about the universe at the smallest scales, except for gravity. Gravity is notably missing from the standard model, and there's a reason for that. You see, the best theory of gravity that we currently have is Einstein's theory of general relativity. And in general relativity, space and time are treated as dynamic. They're both things that can be distorted by the presence of mass and energy. So for example, if we have the Earth here, that's a large amount of mass, which is going to distort the space-time fabric around it. And then if we have another object in the vicinity, let's say this satellite, well, it's going to move through that distorted space-time. So if the Earth were not there, it would continue on moving in a straight line like this. But now in the presence of this distorted space-time, it's going to move in a circular orbit around the Earth. So that's the kind of picture you should have in your mind when it comes to general relativity. So the bad thing is, it appears that general relativity is incompatible with quantum mechanics, okay? Any attempt that's ever been made to combine general relativity with quantum mechanics has led to not only a failure, but paradoxes, just nonsensical results that can't possibly be true. So one of the biggest goals in modern theoretical physics is to find some kind of deeper theory that can unify quantum mechanics and general relativity. So if quantum mechanics includes basically everything we know about the universe besides gravity, and general relativity describes gravity, if we could somehow put those two together, we might have what you would call a theory of everything. And one of the biggest goals in modern physics is to find that theory of everything. So we've reached the end of the lecture. As usual, I have some practice problems at the end, and you can use these to help you study. But I'm going to actually end the video here. So thanks for tuning in, and I'll see you later.